Too cheap? No, too cheap. Too cheap. Too cheap. More on functions. And this just has a few other little added pieces. I'm not going to be talking about the graphs themselves and the intervals of domain, range, increasing and decreasing. So if you run into a checkpoint that says anything about domain, range, increasing, decreasing, skip it for now. We'll deal with it next class. So more on functions. One of them that we're going to have to deal with which actually turns out to be a real-life type function. So it's called a piecewise function. Simplest example. Minutes and money. Minutes and money. If you don't have a phone where you can talk all the time and it doesn't cost you a darn bit of money for all the minutes that you put on it, then this isn't relevant. But if you have a phone where it costs 25 cents per minute for a long distance phone call, this becomes very applicable. So when you start talking about a phone call, at 0 minutes on the phone, you're paying $0 because you haven't even made a phone call. But once your phone call connects, how much do they charge you if it's 25 cents a minute? 25 cents right off the bat. So it jumps up to 0.25. And you get a open circle there. Closed circle means it's included, remember? An open circle means it's not included, therefore this is still a function because the vertical line test is really only hitting the bottom point because it's not hitting empty space. Now as long as you're on the phone for 1 minute, 59 seconds, for 59 seconds, up to 1 minute, 60 seconds, you would only be charged 25 cents. But what happens with 1 minute and 1 second? You get charged for 2 minutes, so then you're up to 50 cents. So it stops here, and it picks itself up here at 50 cents. And it keeps doing this every minute. It jumps up, and it charges you more money. So no matter what happens, if you talk for 1 minute and 1 second, you're guaranteed to be charged 50 cents, even though you only talk one lousy little second over. This is what's called the step function, because it looks like stairs. It is a piecewise function. It has a certain value at 0. It has a certain value between 0 and 1, 1 and 2, 2 and 3, 3 and 4, forever and forever, depending on how long your phone call is. All right, another possibility of piecewise function that's actually relevant to some people if you work on commission, it's not usually straight commission. Usually they have a buffer condition. You have to sell $1,000 before I start giving you commission on whatever else you sell. And they usually have a set pay, so if you didn't sell anything, at least you still get some money for standing around and doing nothing in the store. Yeah, they let you do that, right? So what I want to do is come up with a function that tells you how much Joe should get paid depending on how much merchandise he sells. All right. So what's our variable here? Well, it's going to be x. I'll tell you that. So x is going to represent what here? The sales. How much money he's bringing in. So x equals money in, sales. How much he sells? TV, stereo, so forth and so on. If he only sells if he only sells $1,000, how much does Joe make? $250, because he didn't go over the 1,000. So what you do is you set up a function that has a piece to it. And the pieces are attached with this crazy fancy bracket. And the top one is he earns $250 when X is in this range. I actually might just put it equal to. He could either sell nothing or he can sell up to $1,000, whatever happens. As long as X is between $0 and $1,000, he only earns $250. The trickier part is what happens when he sells over $1,000. So what you do is a little sample. What about he sells $1,200? How would you find out his pay? What would you do?
Multiply by 5%.
Multiply what by 5%? The whole $1,200? The $200. $1,000 doesn't get counted into his calculation. So you're going to take $200. You're going to find 5% of it, which is 0.05. Is that all he gets paid? Plus the 250. So you can kind of get a handle on what's going on by doing it with a physical number. See what you do with the physical number, and then just go back and do it with a variable. Where did the 200 come from? So X minus 1,000. So that's going to be part of it. X minus 1,000. What do I do with X minus 1,000? No, I don't. You take 5% of it, and then add it to 250. We'll simplify that ugly expression. It's not very pretty. So let's see. This is 250 plus 0.05x minus 5% of 1,000. 50. You sure? Because I can't do calculation. You did this already.
No, I did on my calculator.
Cheater. 5 out of 100. 2 of the zeros go away. 5 times 10, 50. So this becomes 0.05x plus 250. So that's what's going to go in the second part of this. 0.05x plus 250. And this is for when x is over $1,000 in sales. So this function would determine or tell you how much Joe is going to get paid depending on what x is equal to. So, question number 1. What's f of 900 equal to? Interpret it. Joe sold $900 worth of merchandise. How much is he going to get paid? $250. Why? Because 900 falls between 1,000 and 0, so the only thing you're going to look at is 250. This one doesn't kick in until he makes over $1,000. So if I do f of 5,000, which function do I look at? The bottom one. So this will equal 0.05 times 5,000 plus 250. Want to do my mental math? This will be 5 times 50, which is 250 plus 250, 500. So this would be $500. Yeah.
Okay, here we got 250 plus that. Wouldn't that be 250 minus 50, so it'd be 200?
I'm an idiot. You're right. I was thinking 200, and I wrote that number down here. This is 200. And therefore, this is 200. And therefore, this is 200. Therefore, this is 450. We're chipping Joe. Joe wants the mistake. He wants more money. But yeah, 250. Why didn't you catch that earlier?
How is that?
It's 250 minus 50. 200. From 0.05 times negative 1,000. But I did the calculation. I came up with 200 in my head, but I was looking at this number and I was just copying. You should copy too. I make mistakes. So this is what's known as a piecewise function. And it is all determined by this part of it, the domain part. This is the domain part. It tells you which piece to look at for certain values. Like if your phone call is between 2 and 3 minutes, the piece you would look for is 75 cents, not the other two. You wouldn't care about them. You only care about how much you're getting charged. All right, so that's piecewise functions. Not that hard. Next little topic. I'll erase it here now. Oh, no, this one's going to require the whole board. It is going to take up most of the time. What's left? There's not that much left. Yeah, I'm running out of time as it is. We're going to go back to this picture. And some funny little graph. Let's call it f of x. The book doesn't do it this way, but I think it's more relevant if you see it this way. It makes kind of sense in a way, instead of just giving you a formula and letting you go with it. If this is f of x and I pick this point here to be a, what does the coordinate on the graph become? This is x equals a. What's the point become? Do you remember? The x coordinate is a. The y coordinate is f of a. Alright, this is just a review of what we did last time. If we move over here someplace and call this b and go up to the graph, this coordinate will be b comma f of b. And then I said, well, that's 2 points in a piece of graph paper. You should be able to draw a line on it and find the slope of that line. And I told you this was a secant. What's called a secant. And the way we found the slope of the line was change in y over change in x. This is where the average rate of change comes from. F of b minus f of a and b minus a. So this is f of b minus f of a and b minus a at the bottom. So that's one way of finding the average rate of change of a function. But there is another way. And it's actually a little bit more powerful and not so nice algebraically. Same graph. Well, I'll try to draw it the same. And instead of picking an A and a B, I want to set up my picture so that I'm only picking a variable. Let's call it x. So when I look at this point up here, this is going to be x comma f of x, the function evaluated at that x value. So that would be a perfectly fine coordinate. Then I'm going to do some trickery. And the trickery is this. I'm going to push away from this x h units. Now h can be positive or negative, but most people push it to the right, make it positive. If I push over h units and I end up over here someplace, what is the value of the x coordinate here? X plus h. You started off with x, you moved h units to the right, that just becomes x plus h. Okay. You go up to the graph, plot a point. The coordinate of this point is going to have an x coordinate of x plus h and a y coordinate of, well, if this has an x coordinate of a and this becomes f of a, and this one has a b and this is f of b, this is x, that's f of x, this is x plus h, this is f of x plus h. It's whatever the x coordinate is, even if it's ugly. Yeah, we don't care if it's ugly. So if I try to find the slope of my secant line this way, it looks a little bit like this, but not a lot. It has some similarities. So you do change in y over change in x. And you get f of x plus h minus f of x for the y values. So f of x plus h minus f of x, all divided by, well, the x values now. X plus h and x. So you get x plus h minus x. Now, where the average rate of change formula, I guess you could call it, has a subtraction in the top and a subtraction in the bottom, the nice thing about this one is when you do the bottom, you get x minus x, which is 0. And all you're left with is h. So this becomes f of x plus h minus f of x, all divided by h. This is called the difference quotient. Difference quotient. you ever get to calculus, this becomes extremely important. Because eventually you take the secant line and you change it into something else called a tangent line. But you don't get to learn that. And you can say, thank God.
Mm-hmm.
But we are going to use this. So, for instance, we'll start off easy. Find the difference quotient of g of x equals 4 minus 5x. Now this one you have to go by formula. Where the average rate of change, you can just find two coordinates and find the slope that goes between those two coordinates. The difference quotient is a little bit different. It doesn't spit out a number, it spits out a function. It spits out another kind of an expression. So we need to find all the pieces, and the pieces are the function evaluated at x plus h, right? The function evaluated at x, we should already have that, and then we're just dividing by h. So the only piece you're ever going to be missing is that f of x plus h piece. It's the only one you have to go searching for. So, how do I find g of x plus h? So one piece I'm missing. How do I find it? No. This is pretty much saying, replace x with x plus h. So on the other side of the equation, I should take this x and first replace it with, what have I always replaced my variables with? Parentheses. Don't even worry about what's going in. Get those parentheses in place so you can put something inside of them. So this becomes 4 minus 5 times something. Once you get it set up this way, I've seen people do 4 minus 5x plus h. And then they put the plus h like at the very end of the expression. It needs to go inside the expression. So whatever goes in the first set of parentheses also goes in the second set. So this also gets x plus h. And then you simplify it. It becomes 4 minus 5x, well, expand it, minus 5h. So there's g of x plus h. Plug the rest of the formula in. It's going to be g of x plus h minus g of x divided by h. So g of x plus h minus g of x, all divided by h. Notice anytime I'm doing substitution, I'm putting empty parentheses so I have some place to shove the junk into. Also because of that minus sign, it gets a little tricky because that has to distribute through whatever I put over there. Alright, so g of x plus h is 4 minus 5x minus 5h. That goes in the first spot. What goes in the second spot? 4 minus 5x, the original function, and then it's all divided by h. And then all you have to do is simplify. And it's actually kind of nice. On the left-hand side, the left piece has a 4, the right piece is going to have a negative 4. Those are going to cancel. The left piece has a negative 5x, the right piece is eventually going to have a positive 5x. They're going to cancel. So all we're left with is negative 5h divided by h. And negative 5h divided by h is negative 5. So that's saying the slope of the secant line for this function is constant, which makes sense because what is 4 minus 5x? How would you graph it? Which makes it a, begins with an L, linear, which makes it a line. And the slope of a line is always constant, negative 5, any point you talk about. So that's the difference quotient. Alright, so let's finish up. What's the difference quotient? 2, 2? Yeah, 2, 2. So, 2, 2 continued. Difference quotient. And last time I showed you where the difference quotient came from. because it's the same thing as the average rate of change formula. Interesting. Yeah. Better not write low. It's the slope of the secant line of a function, just with a different way of looking at it rather than the average value. And we did an example of a average rate of change of a line, and it came out as a constant. Remember that? Yeah. No, probably not. So what I wanted to do is the other three examples that are in the homeworks. One of them is just a polynomial, quadratic. And I want to find the difference quotient of this quadratic. And the steps are pretty simplistic. The only thing that you do not know about with the difference quotient is that f of x plus h piece. So the only thing you have to go and find is f of x plus h. So you take your function, skeleton form it, and then plug into what into each one of those parentheses? X plus h. So f of x plus h is equal to 3 times x plus h all squared minus 3 times x plus h plus 2. And then you have to take this ugly expression and expand it. So let's check out your polynomial tricks. So f of x plus h on the right-hand side, or left-hand side, equals, what is x plus h all squared? You can't distribute the 3 first because powers have to come before multiplication. So what's x plus h all squared?
X squared plus x,
2xh
plus 2h.
plus
H squared.
h squared. So you get 3 times x squared plus 2hx plus h squared. And I'll leave the rest alone for now. I like doing all my distribution at one time. All right, and then you distribute. So you get f of x plus h is equal to 3x squared plus 6hx plus 3h squared. You know what's funny? The biggest mistake for people here is that h squared. They forget to give it the number that's in front. They'll distribute to the first two, and they'll forget all about the third one. I don't know what it is. I think people are used to distributing over binomials rather than trinomials, so try to be a little bit careful. Then the minus 3 goes through, so you get minus 3x minus 3h plus 2. And that gives you the first chunk of the difference quotient. That's just the first piece. The second piece of the difference quotient is your original function. So that's the first piece, the blue part. The black part is the second piece, and then you divide it all by h. You just divide it all by h.
Or you did the negative 3 and it's supposed to be negative 5. The second one.
Did I screw up? I screwed up. Couldn't have caught it earlier, could you?
Well, I was looking at myself and my answer.
Yeah, it's supposed to be negative 5 here. So negative 5, negative 5. So this is negative 5x and negative 5h. There we go. How's it look on here? Horrible, but that's okay. So now that it's corrected, we can plug it into our formula. So f of x plus h minus f of x, all divided by h. So f of x plus h is that ugly mess that I just came up with and corrected, is 3x squared plus 6hx plus 3h squared minus 5x minus 5h plus 2. Bless you. So there's f of x plus h, taking care of that first position, minus, and I always replace things with parentheses. If I'm substituting something in, I'll put parentheses first and then show the stuff inside of it. So minus whatever comes next is f of x itself, which is, where is it? There it is. 3x squared. Oopsies. You think I can see that far? I'm old.
Minus 5x.
No, but-
That's 2.
And divide the whole thing by h. Now, if you remember the one that we did on Monday, it looked like everything canceled out and then we can simplify what was left over. Same thing's going to happen here. Here you have a positive 3x squared. Eventually here you're going to have a negative 3x squared. So if you add them together, what happens to those two? They cancel rather nicely. Over here you have a negative 5x. Over here you're going to have a positive 5x after you distribute the negative. So these two are going to cancel rather nicely. Here you have a positive 2. Here you're going to have a negative 2. So these two are also going to cancel. So one of the properties of the difference quotient of a polynomial is your original polynomial is going to cancel. The whole thing disappeared at 3x squared minus 5x plus 2. They all cancel. And what you're left with, each of them has a h, which is really good because there's an h in the bottom. Alright, so let's simplify this. This is 6hx plus 3h squared minus 5h all over h. Is that the best I can get it?
6x plus 3h minus 5.
You can remove one factor of h out of everything. You could factor out an h in the top, the two h's cancel, or you could just imagine h dividing into each one of the individual pieces in the top. This is a nice little expression. The original expression had that h in the bottom. Eventually what you want to do to h is shrink it down so small that it gets really close to what number? How far apart are my fingers? 0. And the problem with h in the bottom here is you're dividing by 0, but here you're not. So this is a weird thing where it's calculus based, but the idea is you get to divide by 0 in calculus, which is kind of cool if you think about it. But this describes the slope of a secant. This slope of a secant is dependent on what h is equal to. Well, h and x, basically. If you have an x-coordinate and you have an h distance away from that x-coordinate, that'll give you the slope of the secant line. So dependent on h and x. Where the average rate of change is dependent on two x's, this one's dependent on one x and a certain distance away from the x, whatever you want it to be. Isn't that neat? Is it going to be on the test? How many of these? Enough to make you sweat, just like word problems. How many word problems on the last test? 4. Did I lie? How many did I say there were going to be on this?
7.
I did say 7?
Mhm.
I was nice. I reduced it down to 4. Supposedly 4 of the easiest ones. Didn't seem that way though. Yeah, they were. I could have put harder ones on there. A little harder for difference quotient. G of x is equal to x over 2x minus 1. A rational function. This is not going to be pretty, but I do have some neat little tricks that will make life a little bit easier. Polynomials are the ones you have to do the work in the beginning, and then it gets easier as you go. Rational and radical, the beginning is really easy, and you have to do the work to get to the end. So the work just shifts a little bit. But you start off the same way. You want to find g of x plus h. But the first thing you do is you go through your original function, and you replace every x with an empty set of parentheses. This is how you get used to working with functions. And it helps you not to make silly little mistakes. What goes in every one of those parentheses? X plus h, because I want to find the first part of the difference quotient. And you get that expression. New function. Alright, I need to simplify what's there. There's not much I can simplify, so this is going to become g of x plus h is equal to x plus h over 2x plus 2h minus 1. That's it. The best I can do. All right. So there's g of x plus h. Remember the formula, whether it has f in it or g in it, that's irrelevant. Remember, it's just Frank and George to begin with. So if you want, the formula for this one is going to be g of x plus h minus g of x all divided by h. It's irrelevant what letter you put in front. All right, so first piece first, g of x plus h. I don't think I need parentheses. Let me get rid of that. The long fraction bar will take care of the parentheses. So we're going to get x plus h over 2x plus 2h minus 1. There's g of x plus h. Minus the second part of the formula, which is just g of x itself, the original function, x over 2x minus 1, all divided by h. So it's f of x, or in this case, g of x plus h minus g of x divided by h. So, kind of like the polynomial one, I'd really like to get that h out of the bottom. Because if I can get rid of the h out of the bottom, then I can make h as big as I want and or small as I want. Let it go to 0 and it'll be perfectly fine. So what kind of fraction is this thing called? Does anybody remember? Well, double fraction is one way of naming it. Complex fraction is the best way of naming it. It's really looking quite complex. All right, do you remember how to solve equations with fractions in it?
Yeah.
You multiply both sides by
The denominator.
common denominator. So whatever you did to the left, you do to the right. Well, fractions kind of work like that, except they work in the way that whatever you do to the bottom, you do the same thing to the top. So if you look at this, what is the common denominator? Now remember, h is just over 1. Well, 1's part of the common denominator, sure, why not? What else is in the denominator?
1/8. I mean,
This h is not this denominator, the denominator of each one of the fractions.
oh, it needs a 2h.
It needs a 2x minus 1. What else?
Over h.
Nah, 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 nah.
2h plus 2h.
The 2x, the plus 2h minus 1. These things aren't the same. They're totally different. Even though they have some of the same pieces, they're totally different numbers. So what I'm going to do is, this works for complex fractions. Whatever you do to the top, you do to the bottom. And what I'm going to do is multiply by 2x minus 1 and 2x plus 2h minus 1. What that'll do is get rid of all the complexity of the fraction. But whatever you do to the top, you have to do the same thing to the bottom. Because by doing that, you're just multiplying by a fancy 1. And 1 times anything is itself. All right, well, when you distribute these two chunks to that first piece, what goes away? The 2x, the 2h, the minus 1. They're exactly the same, so they'll cancel out on both sides. What's left over is x plus h times the other one, which is the 2x minus 1. All right, minus, when these two run into each other, what goes away? The 2x minus 1s, and you're left with that factor of x in the top, times 2x plus 2h minus 1. 2x plus 2h minus 1. All over. Get out of the way for a second. The bottom is actually worse than the top, but at least you just have to copy it. Nothing cancels in the bottom. You're left with h times 2x minus 1 times 2x plus 2h minus 1. All right. What can I do with that? How so? Cancel what? Please do not tell me you're going to cancel bottom and top. Why can you not cancel anything in this fraction? That minus sign is locking everything in. Now, if you want, you can separate the fraction and cancel, but all that does is bring you back. Yeah, you don't want to do that. So the best thing you can do is just take the top and expand it. Get rid of all the parentheses so you can see what's going on. So FOIL that first one out, distribute the second one out, and see what happens. So x times 2x, 2x squared. What is it?
Minus x, minus x, minus h.
Minus x
Minus x,
minus h.
minus x.
Okay, you lost me. It's 2x
Minus
squared
x.
minus x minus h and then a plus 2hx. Oh, you went out of order.
Oh,
First, outer, inner, last. First, outer, inner, last. Oh well, it's out of order, but it doesn't matter. Distribute the negative x, so you get negative 2x squared, negative 2hx, and positive x. All over h times 2x minus 1, 2x plus 2h minus 1. Which one would you rather do, polynomial or this one? Trust me, polynomial seems more natural for most people. But the same thing kind of happens here. Here you have a 2x squared. Here you have a negative 2x squared. What's going to happen? They're going to cancel. Here you have a positive x. Here you have a negative x. They're going to cancel. And everything else that's left over just has an h in it. So you're going to get negative h plus 2hx minus 2hx. Oh, wait a minute. Oh, they cancel out too. Isn't that nice? All over h, 2x minus 1, 2x plus 2h minus 1. It's awesome. More canceling. Let me kill them with green markers. Now they're gone. Wish I had red. It would look better. Alright, now once those two are gone, you have h over h here. So I can cancel those and make it just a big fat 1. What's left in the top?
1 over
Just 1 over?
negative.
Negative 1. So it's negative 1 over a, oh no, there's no h there. 2x minus 1, 2x plus 2h minus 1. Now if I let h equal 0, it actually becomes perfectly fine. It doesn't cause any problems. And again, that's the slope of the secant line, depending on whatever x value you give it and whatever h value you give it.
You want an formula or whatever on
What's
the
that?
bottom. You want an
Don't expand that. Leave it just like that. Because what happens is, when you let this equal to 0, then this becomes 2x minus 1 times 2x minus 1. Better known as 2x minus 1 squared. It's much better that way. Yeah, just leave the bottom alone. Tops are what you mess with fractions, polynomial-wise. Bottoms you usually generally want to leave them in factored form. Tops you change, bottom.
Well, what if you go on and like factor that out?
Please don't. Don't multiply those two. Just leave them. Just leave them. Trust me. Just leave them. The work that happens in fractions is always in the top. When you're adding.
Yes, okay.
You see what I'm saying?
Mm-hmm.
And also, if you simplify the top and it happens to be one of these factors, then you can cancel it.
So how you know when to stop at the bottom?
Oh,
Like when not to go any further?
once you get rid of those h's, stop. Once the h in the bottom is gone, you can stop completely because that's the end.
But H is still on the bottom.
I know.
Top.
This h doesn't cause a problem. Not like this h over here. Because you can't let this one equal 0, but this one you can let equal 0 and it's perfectly fine. So what I'm talking about is that h. As long as he's gone, you're perfectly fine. The next one takes up just as much room, so I have to start from over here. I'll do that for now. Last one. No, I better not call it that. M of x. M of x. Another difference quotient 1 is equal to the square root of 3x plus 2. M of x. Michael. Same first step. We need to find m of x plus h. M of x plus h. So you go through and wherever you see an x, you replace it with parentheses. What goes in the parentheses is x plus h. again, there's not a lot of work in the beginning of this one. It's mostly at the end. So you expand it out and you get your m of x plus h. So m of x plus h is equal to the square root of 3x plus 3h plus 2. And then you plug it into the formula. So it goes, I don't need a parentheses again. The radical takes care of it with that straight line on the top. Back this off. There we go. So the square root of 3x plus 3h plus 2 minus the original function, all divided by h. So the initial setup isn't too bad with this. It's what happens next that a lot of people don't like. Can I get rid of the h in the bottom yet? Nope, it's stuck. So I got to do something. So what trick do you know with radicals frees up things? Squaring would work great if there was another side. There's no other side. This is just a simple expression. So you can't use the square trick. Any other little tricks up your sleeves? Begins with a C. C-O-N? Conjugate. Conjugate this thing. What is the conjugate of this mess up top? Well, it's this mess up top, except this minus becomes plus. So you see radicals, two separate radicals or a radical and another number added together, your first thought really should be conjugate to simplify it. All right, so we're going to multiply top and bottom by the conjugate of that mess. So it becomes the square root of 3x plus 3h plus 2 plus the square root of 3x plus 2. Top and bottom. Conjugates. A wonderful thing. Now remember the property of conjugates. The middle two, the O and the I in FOIL, they cancel each other because one will be positive, the other one will be negative, and they'll be exactly the same. They'll be opposites of one another. So the only things you have to multiply together are the first and the last for the top. The bottom we're not going to do a darn thing to. We're just going to leave it alone. Because just like the other one, just leave the bottom alone. So when the first run into each other, what happens to the radicals? Oy, break fingers. What happens to the radicals? What's the square root of 5 times the square root of 5? 5. Square root of 7 times the square root of 7? 7. Square root of 3x plus 3h plus 2 times the square root of 3x plus 3h plus 2. 3x plus 3h plus 2. The radicals kind of go away, like you're squaring it. But in this case, you are really squaring it, but we're multiplying it by itself. We don't have to worry about the outer and the inner because they're exactly the same, and one's positive and the other one is negative. So the other multiplication we do is last. And they're exactly the same. And they're also going to pop the radical off, but be really careful. It's going to be minus whatever happens next. In this case, 3x plus 2. The square root of 3x plus 2 times the square root of 3x plus 2 is just 3x plus 2. But this minus sign is eventually going to come through there. And then the bottom doesn't change. It stays its little ugly form. I wonder if there's an easier way to get to the answer. It's taking too long, isn't it? Okay, nice things again happen in the top. Things are going to cancel. Here you have a positive 3x. Here you're going to eventually have a negative 3x. So those two pieces are going to cancel. Here you have a positive 2. Here you're eventually going to have a negative 2 after you distribute that negative. Those are going to cancel. What's left? You have a 3 and an h in the top and an h in the bottom. What happens to the h's? The h's. H's. Wake up. What are they going to do? They're going to cancel because you have an h in the top and an h in the bottom. They're just going to cancel. So what's left in the top after the h's go away? 3 over the square root of 3x plus 3h plus 2 plus the square root of 3x plus 2. And that would be your final answer because those h's finally cancel. Ta-da!